So this is joint work with Sergey Bravi at IBM, Dan Brown and Porrick Kalpin at UCL, and Earl Campbell and Mark Howard at Sheffield. And we were supported in part by NQIT. Okay, so let me begin by saying a few words about the motivation for simulating quantum circuits on a classical computer. So I think most of us, or all of us, believe that quantum computers can't be efficiently simulated by classical computers. So why should we study classical simulation algorithms? I can think of at least three reasons. First, we might wish to quantify the classically hard resources in quantum computation and understand which restricted quantum computations are easy to simulate or easier. Secondly, we might wish to verify and validate small quantum computers like the ones that are currently being built. And thirdly, it's useful to poke at this belief a little bit and give ourselves confidence by continuing to try to simulate quantum circuits in different ways. Okay, so let me now define some classical simulation tasks that you might wish to perform. So here is a quantum circuit acting on the all zeros initial state, followed by measurement of all the qubits. The measurement produces a bit string, an n-bit string z, with probability distribution given by p of z. So one task you might consider is to what is usually called strong simulation, where you're given a bit string x, and the goal is to compute the probability of that bit string in the output distribution. And this task is sharply hard, and this is not something that quantum computers can do efficiently, but certainly it's something we could consider doing on a classical computer. A second task is often called weak simulation, and in this task, the goal is to sample a bit string from the distribution p. I'm going to be a little bit sloppy here. I mean, really what I mean here is to approximately sample from the distribution p. So I will allow myself, for example, an inverse polynomial total variation distance difference between the sample distribution and the actual distribution. And this is something that quantum computers can do. So this is a more realistic goal in terms of simulation. And it will also be convenient to define a variant of strong simulation, which we'll call epsilon strong simulation, where we're given a bit string, and rather than computing the probability exactly, we just ask for an epsilon relative error approximation. So this is still sharply hard, and quantum computers can't do that. Okay. So most algorithms for any of these tasks most classical algorithms have exponential scaling in the number of qubits or the number of gates. The sort of naive algorithm would be to represent a quantum state as a complex vector with 2 to the n entries and perform sparse matrix vector multiplication to perform each gate. And this obviously has runtime exponential in the number of qubits and also requires an exponential amount of memory. Another algorithm would be based on expressing a circuit amplitude, just writing out the matrix multiplication, or if you like, you could call it the Feynman path integral. And so by inserting complete sets of states after each gate, this one obtains a sum with lots of terms, an exponential number of terms, but where each term is easy to compute using a small amount of memory. And there are recursive variants, or there is a recursive variant of this, which was proposed by Aronson and Chen in 2016, which has better performance in terms of the scaling with circuit depth. And that can be viewed as along the lines or a continuation of work that was started in 2005 by Markov and Shi, whereby classical simulation is viewed as a tensor network contraction problem. And one aims to contract the tensor network representing a quantum circuit using an ordering of indices that reduces the runtime and memory requirements. And these tensor network contraction methods have been very successful, especially in recent years, in simulating two-dimensional quantum circuits that are similar to the types of circuits that might be implemented on near-term devices. This table is from a paper by the Alibaba group, Chen, Zhang, Huang, Newman, and Shi, and lists several of the recent simulations of quantum circuits, including this simulation which is on a grid of 9 by 9 qubits and with a depth of 40. One important point here is that the number of amplitudes is only 1 here. So if you wanted to compute more amplitudes, there would be an overhead. And if you wanted to sample from the output distribution, there would also be an overhead associated with that. But these are obviously very impressive simulation results. One interesting observation which was made by Huang, Newman, and Segedie is that these methods, the tensor network contraction methods, have a feature which they called monotonicity. They call them monotone simulation methods. And at some level, what this means is that they don't make use of the structure of the quantum gates. They're sort of, any tensor network with gates that appear or that are contracted in that sort of geometry would have the same runtime scaling. And this places limitations on the performance of these methods. And in particular, Huang, Newman, and Segedie show a lower bound of 2 to the n minus little o of n in terms of the runtime of any monotone simulation method for general quantum circuits. And so this talk is about an alternative to the tensor network contraction methods, and it's a different type of simulation algorithm which succeeds in a different regime and happens to also not be a monotone simulation method. Okay, so this brings me to the next part of the talk, and mostly what I'll talk about here, I will just review the simulation of Clifford+T circuits based on stabilizer rank, which sort of comes out of these papers. But I also want to mention lots of related work on extending the Gottesman-Knil theorem and sort of the resource theory of magic states. Okay. So we all know the Clifford group, which is generated by the single qubit Hadamard phase and controlled NOT gate, and the Gottesman-Knil theorem, which tells us that we can simulate the circuits composed of Clifford gates efficiently on a classical computer. And so the simulation methods that we'll be interested in extend Gottesman-Knil to circuits with a small number of non-Clifford gates. And in this case, for this part of the talk, we'll be talking about circuits with a few T gates. So in particular, we'll consider the Clifford+T gate set. So we have the Cliffords and we have the single qubit T gate. And we'll ask, what is the classical simulation cost of a circuit with m T gates? We know that if m is 0, it's efficient. And then if we have 1 or 2 or m, what's the cost? So the strategy from these previous works is first to gadgetize the Clifford+T circuit. So this is a gadget which implements a single qubit T gate. On the right-hand side, the gadget has only Clifford gates and classical measurement and control. And it also makes use of a resource state, written A here, which is called the magic state. This is a non-stabilizer resource state which is consumed by the gadget. So if we take a Clifford+T circuit with m T gates and we replace each T gate with this gadget, we get an adaptive Clifford circuit, meaning there are intermediate measurements. And the input state is all zeros and then a bunch of magic states, m magic states, if we have m T gates. So then this reduces the problem of simulating a Clifford+T circuit to the problem of simulating this gadgetized circuit, which has this form. So here on the left is there are some magic states, the all zeros initial state. We have a Clifford operation which contains measurements. So the number of qubits in is not the number of qubits out. And then we measure some register of double qubits at the end. And the simulation strategy, and this is sort of a meta strategy which tries to encapsulate what's done in all 3 of these simulation tasks I discussed earlier. And so the strategy is basically as follows. The goal is to first approximate the input magic state as a superposition of a small number of stabilizer states, then apply the Clifford operation to each term in the superposition, and then simulate the final measurement somehow. So that's kind of the high-level strategy. And you can ask, what is the runtime of this? And it depends on the simulation task that you're considering, but at least for these 2 steps, the runtime is linear in chi up to polynomial factors. And for this step, at least for weak simulation, we have a way to make the simulation of the final measurement also linear in chi. Okay. So what you should ask at this point is, if we need to approximate this input magic state as a superposition of a small number of stabilizer states, what kind of approximation is needed and how big is this chi, because that determines the runtime of these algorithms. And so that brings us to the definition of stabilizer rank. So the stabilizer rank of some state psi is the minimum number of terms in a decomposition of psi as a superposition of stabilizer states. Likewise, we can define the approximate stabilizer rank, which has a precision parameter delta, and it's defined to be the minimum number of terms in a decomposition of psi as a sum of stabilizer states that approximate psi to within delta. Okay, and just to conclude the review portion of this talk, the cost of the existing stabilizer rank simulators for Clifford+T circuits, these costs scale with the stabilizer rank of the magic state input. And so if you have m T gates, n qubits, and g total gates, for strong simulation, the cost is quadratic in the stabilizer rank. For this related task of epsilon strong simulation, where we only ask for a relative error approximation of the output probabilities, this can be brought down to linear in the stabilizer rank. And for weak simulation, the cost is linear in the approximate stabilizer rank, which can be much lower than the exact stabilizer rank. And if we substitute the best known upper bounds on stabilizer rank, we get these costs as a function of the number of T gates m. So obviously these are exponential in m, as they should be. We don't expect to be able to simulate m T gate circuits using polynomial cost in m. But on the other hand, we don't have good lower bounds on the stabilizer rank, and that remains an open question. What I mean by good is a lower bound which scales super polynomially with m. So the best lower bound which is known scales as square root m, and that comes from this Bravi, Smith, and Smolin paper. Okay, so now in the second part of the talk, I'm going to tell you about some of our new results, and in particular, generalization of this simulation algorithm to other gate sets beyond Clifford+T. So the tool that we use in the new simulation algorithm is very simple, and we call it a sparsification of stabilizer decompositions. So let's consider a stabilizer decomposition of some state psi which is normalized. So this is just an expression for psi as a sum of stabilizer states. What this sparsification lemma says is that the approximate stabilizer rank of psi, let's forget about this precision parameter for a moment. Imagine it's a small constant. So then what this says is that the approximate stabilizer rank is upper bounded by the one norm squared of the coefficients appearing in this sum. And the proof of this lemma is constructive, meaning we can start from this exact decomposition, and then we can produce an approximate stabilizer decomposition of psi with this number of terms. Okay? And the proof is very simple. Maybe you could already guess what it's going to be. We consider a random state where we sum L stabilizer states, and each term in the sum is independently chosen to be one of the terms in the original decomposition of psi, and they're chosen with probabilities proportional to the magnitudes of these coefficients that appear. And then it's a simple calculation to show that the expected norm difference squared between the state we want and this random state is actually equal to the one norm squared divided by the number of terms L. So this number of terms L is, of course, the stabilizer rank of S, and if this quantity is small, then L becomes the approximate stabilizer rank of psi. And it's from this expression we see that it suffices to choose L to be given by this quantity to make the error what we want. Okay, so that's kind of how that goes. And we can use that to perform weak simulation of circuits that are composed of Clifford gates and single qubit Z rotations. So on this slide and the next couple slides, I'm going to use green to denote Cliffords and red to denote non-Cliffords. And we're going to consider these single qubit Z rotations, and they have a parameter which is the rotation angle, and that can be anything. If you take pi over 4 to be the rotation angle, you get the T gate, but this obviously contains a wider class of quantum circuits. Here's an example, and these angles are unrestricted and can be different for the gates that appear in different parts of the circuit. And so now the simulation strategy is a little bit different because we can't gadgetize the circuit like we did before. So instead what we're going to do is we're going to use the sparsification lemma to directly approximate the output state by a superposition of few stabilizer states. And then we're going to simulate measurement on this approximation using, well, we could use, for example, the existing algorithm for simulating measurement for low-rank stabilizer decompositions. Okay, so on this slide I'm going to tell you the basic simulation algorithm, which is quite simple. So we're going to take a single qubit Z rotation, the type of gate that the type of non-Clifford gate that appears in our circuit, and we're going to write it as a sum of two Cliffords, the identity and the single qubit phase gate. And if you write it in this way, these are the coefficients. Okay, but now if we have a circuit that has m non-Clifford gates, so we have a Clifford followed by a Z rotation followed by a Clifford, Z rotation, and so on, then we can insert this expression for each of the non-Clifford gates, and we'll get a sum of 2 to the m Cliffords acting on the input state. So on the right-hand side here, we have a sum over 2 to the m stabilizer states with coefficients that are determined by the coefficients that appear in this equation above. So now we can apply the sparsification lemma, which tells us, you see, up here we have an exact expression for the output state of the circuit as a stabilizer decomposition with lots of terms, but if the one norm of the coefficients is small, we're happy because we can sparsify this stabilizer decomposition to obtain an approximation of this state with a number of terms that's given by the one norm squared. And so if you evaluate that quantity, this is what you get. So this is the approximate stabilizer rank of the output state of this or it's an upper bound on the approximate stabilizer rank of the output state. And now you might ask, how does this compare to the upper bounds on the approximate stabilizer rank we have for circuits with m T gates? And in fact, it coincides with that upper bound if you take all of the gates in the circuit to be T gates. So this strictly generalizes that previously known upper bound. And so once we have this approximation of the output state as a superposition of few stabilizer states, then we can simulate the final measurement in time linear in chi using the norm estimation algorithm from previous work. Okay, so this is kind of like the basic algorithm, which is reasonably simple and somewhat different from the previous algorithm, which involved gadgetization. But because we're interested in our work in also implementing this algorithm and having it work having it work well, we also present a suite of subroutines for manipulating and processing low-rank stabilizer decompositions, which allow us to implement this algorithm in a sort of high-performance way. So one of those subroutines that is needed is a Clifford simulator that's capable of storing stabilizer states and updating them in a representation that includes the global phase of the stabilizer states. So most of the previous Clifford simulators don't have this feature. So that's one thing we need. Another thing that we have in our paper is a simplified version of the norm estimation algorithm from previous work, which has the same asymptotic runtime, which is linear in chi, but has kind of a terrible polynomial factor. But the simplified version achieves a 50 times speed up in practice in our implementation, which is kind of nice. However, it turns out to be better to use, at least if you're interested in implementing this, one thing you might consider is to use, rather than the norm estimation algorithm, which has this terrible polynomial factor of n to the 6, we present a Markov chain algorithm to simulate the final measurement as an alternative. And this sacrifices rigor in the sense that we can run now a Markov chain which converges to the output distribution, but we have no bounds on its convergence time. But in practice, so if you want to simulate t steps of this chain, the polynomial factors are much better if t is not scaling, if t is not too big as a function of n. Okay, so we used our implementation of this simulator to simulate a 50 qubit circuit which implements a quantum approximate optimization algorithm, which is basically a short depth quantum circuit to approximately optimize a classical cost function. So this algorithm was proposed by Farhi, Goldstone, and Gutman, and we simulated a specific instantiation of it applied to what's called the E3 Lin2 problem. But I don't want to say too much about the details of this. All I'll say is that there is a classical cost function, which is diagonal in the z basis. These are Pauli z operators, and these are some coefficients. And the circuit that we're considering is you start in all zeros, you apply a non-Clifford gate, which is an exponential of this cost function with some parameter, some angle gamma that's a free parameter. Then you apply a Clifford gate, which is a tensor product of single qubit Clifford rotations. So the thing that we'll be interested in is the expected value of this cost function at the output of this short depth circuit as a function of gamma. And this is a convenient benchmark because this expected cost function can be calculated by our simulator, where we actually apply the circuit and simulate the measurement of all n output bits. But it can also be computed by other more precise methods that are not as resource intensive. So that allows us to compare our simulator and its ability to sample from the full n-bit output distribution. And we can compare the results of that to something that whose value is known or can be computed more easily. Okay, so that's what we did. We used the simulator to approximately sample from the output distribution of this state, and then we computed the expected value of the cost function as a function of gamma. So here is our results. This circuit contains 66 z rotations, and the angles of the z rotations are all the same, but they, this plot is, the x-axis is the angle divided by pi. On the y-axis is the expected value of the cost function, and in blue are the data points produced by our simulator, and in red are data points produced by a more precise method. It says exact, but nothing is exact. It's more precise. So one thing I'll point out is that the most costly data point here is the one which is closest to gamma over pi being 1/4. So actually the most costly version of this simulator is when all the gates are T gates. But for this data point, the output state in our simulator was approximated using over 1 million stabilizer states. To produce this whole plot took, I think, roughly 2 or 3 days using a laptop. So this is in contrast to some of the other simulations of 2D circuits I showed you before, which used high-performance computers. Okay. And this should be compared with previous numerics for these stabilizer rank simulators, which were applied to a different problem, and which used only about 1,000 stabilizer states and only sampled from single qubit marginals, which is significantly easier than sampling from the full n-bit output distribution. Okay, so that's all I want to say about the simulation and the implementation. And in the last part of the talk, I would like to tell you about some of the more mathematical aspects of our work. And in particular, I want to talk about some measures of non-Cliffordness or non-stabilizerness. In particular, the stabilizer rank and some of its close cousins. So first of all, if you remember the Sparsification lemma, okay, so this quantity we define to be the stabilizer extent of a state psi, this quantity in yellow here. So what is it? For a state psi, you minimize the 1 norm squared of the coefficients that appear in any stabilizer decomposition of psi. So this is the quantity that appears in the Sparsification lemma. In other words, the best possible upper bound on the approximate stabilizer rank from the Sparsification lemma is written in terms of the stabilizer extent here. So in other words, if you optimize the bound in the Sparsification lemma, the right-hand side becomes proportional to the stabilizer extent. Obviously, this quantity is 1 for a stabilizer state and can be much larger than 1 for non-stabilizer states. A related quantity is the stabilizer fidelity, which is defined to be the maximum inner product squared between the state psi and a stabilizer state. But it turns out that these two quantities, the stabilizer extent and the stabilizer fidelity, are closely related. There is a convex duality which relates them, and I'm just going to state this, although the proof is not difficult, So the stabilizer extent can be written as a maximization over states W in the same Hilbert space as psi. And in the numerator, we have the inner product between psi and W squared. In the denominator, we have the stabilizer fidelity of W. So just inspecting this equation, you can see that if you plug in any particular witness state W, then this equation will give you a lower bound on the stabilizer extent. But it turns out that for magic states like the single qubit magic state we talked about earlier, and a broad family of other magic states that I'll call Clifford magic states, then this, the optimal witness turns out to be the state itself for this special family of states called Clifford magic states. And in that case, the stabilizer extent is actually equal to the inverse of the stabilizer fidelity. So these quantities are fairly closely related. Okay, so what am I going to tell you about having to do with these quantities? Well, I mentioned earlier the open question, which is to establish a lower bound on the approximate stabilizer rank of magic states. So in other words, we care about the m-fold tensor product of a single qubit magic state, and we would like to understand lower bounds on the approximate stabilizer rank. But a related question, which maybe is a little bit easier, is to ask how do measures of non-Cliffordness, like approximate stabilizer rank, extent, fidelity, how do they behave under tensor product? So in other words, if we take psi tensor phi, can we relate the approximate stabilizer rank of that to the approximate stabilizer rank of psi and that of phi? And we can ask the same question about the extent and the stabilizer fidelity. And really would like to answer this question for the approximate stabilizer rank, but we can't do that. But we can give a sort of what I would call a complete answer for the stabilizer fidelity. So that's what I'll tell you about next. Okay, so first of all, this is not the complete answer, by the way. This is just the starting point. It's very easy to see that the stabilizer fidelity is actually just not multiplicative. So in other words, if you take a Haar random state psi, then the stabilizer fidelity of psi tensor, its complex conjugate, is strictly larger than the product of the stabilizer fidelity of psi times the stabilizer fidelity of psi star. And the proof of that is basically two lines. The stabilizer fidelity here is, well, okay. The point is that if you compute the inner product between psi tensor psi star and a maximally entangled stabilizer state, then that has anomalously large inner product relative to the right-hand side. Okay, but that's not really the point of what I want to tell you here. We address the question of when is this stabilizer fidelity multiplicative. So let's consider a set S, which is in some sense maximal, and I'll talk about that later, such that f of psi tensor phi is equal to f of psi, f of phi for all states psi and phi drawn from this set S. And so we are able to completely characterize such a set S. And that's what I'm going to tell you about in the last 3 minutes of the talk. So the set that we consider is we call stabilizer aligned states. So I just need a little bit of notation. Let's define the set P sub k of stabilizer projectors which project onto a stabilizer code with 2 to the k basis vectors. Okay? So if k is 0, this is just one stabilizer state. And we say that a state is stabilizer aligned if the following equality holds for all k from 0 to n. So on the right-hand side, we have the stabilizer fidelity. That's the maximum inner product squared between psi and a stabilizer state. And on the left-hand side, we have a maximum overlap between psi and a stabilizer code projector of dimension 2 to the k. But then we have this really funny square root, okay? So if this square root was replaced by 1 over 2 to the k, this would always hold, because this is a projector onto 2 to the k states, and each one has to have inner product with psi at most the stabilizer fidelity. So this would hold trivially if we didn't have this funny square root, but the definition that turns out to be useful here has the square root, so it is what it is. Okay, so that's stabilizer alignment. And what do we prove about this? I said we were going to sort of give a complete solution. So we proved that first of all, if you have 2 stabilizer aligned states, then the stabilizer fidelity is multiplicative. So that's the first thing. The second thing is that if you have a state which is not stabilizer aligned, and you take psi tensor psi star, then the fidelity is not multiplicative. And the final thing, which is kind of remarkable, is that the set of stabilizer aligned states is closed under tensor product. So if psi and phi are both stabilizer aligned, then so is psi tensor phi. Okay. Now the proof of this, so 1 and 3 are the hard parts, and 2 is kind of easy. And to prove 1 and 3, actually they both follow from a single inequality, which is I've written here, and it has this parameter k, and so you have to prove this for all k from 0 to n. Actually, it's not hard to see that 1 and 3 follow from this, but in the interest of time, maybe I'll move on. One thing I will mention is that the proof here really leverages this result of Bravi, Fatal, and Gottesman, which characterizes the structure of entanglement in bipartite stabilizer projectors. And so you can view this as a consequence of that result from 2006. Okay. So a useful corollary is that if you have a set of stabilizer-aligned states, then the stabilizer fidelity just decomposes into the product of the stabilizer fidelities. And now you can ask which states are stabilizer-aligned, or like, are there any useful ones? And so a simple observation is that all single qubit states have this property. And we prove in our paper that all 1, 2, and 3 qubit states have this property. So it's an open question whether one can find, what is the smallest number of qubits where there exist states that aren't stabilizer aligned. But just putting everything together, what it says is that if you have any set of 1, 2, and 3 qubit states, then the stabilizer fidelity just decomposes into a product. And convex duality implies directly the same thing for the stabilizer extent. And so I'll end there with some open questions, and I think I'm over time, so I'll let you read those, and hopefully we can have some questions. Thank you.
Thanks a lot, David. Are there any questions?
Yeah. Can you give us a sense of why your Markov chain algorithm doesn't encounter complex amplitudes?
It's a Markov chain Monte Carlo algorithm for simulating from the output distribution. So it doesn't have to do with the state, it just looks at the distribution. Yeah.
Okay.
To what extent is the algorithm parallelizable?
I don't know off the top of my head. Yeah,
Okay.
that's a good question. Yeah.
Sorry, could you repeat the definition of stabilizer aligned?
Yes. Hold on. There it is. So this pi is a projector onto a code space of a stabilizer code with 2 to the k basis vectors. And this F is the maximum inner product between psi and a stabilizer state all squared.
Can you give some, that there's no intuition for this? Or?
Well, honestly, not really.
All right. And again, it might be that all states are stabilizer aligned?
No, because we know that for n sufficiently large,
Yeah.
there are non-stabilizer line states because the stabilizer fidelity is not multiplicative.
Okay.
Yeah.
Well, so can you give some examples?
A Haar random state with n sufficiently large.
Okay, good, good. But you don't have an explicit example.
No.
Okay, thank you.
Mm-hmm.
Cool. Maybe one more question?
Is it possible to apply this stabilizer decomposition technique to simulating like random circuit sampling, or how does it compare to tensor network contraction techniques?
Yeah, I mean, I think that's a good question. I think one challenge is that those circuits tend to have, like the circuit we simulated had hundreds of Cliffords, but it had 66 non-Clifford gates. And so if you have a circuit with a lot more non-Clifford gates than that, you might be outside the regime where these techniques are useful. Yeah.
Awesome. Let's thank David again.